Yeah, this is instructor Dave Rahija, and I'm a safety and reliability consultant for aerospace, consumer, medical, and even hospitals, where they kill 445,000 patients a year from mistakes. But my primary field is engineering, and I teach at the University of Maryland course on design for safety and another course designed for reliability. And I've been in consulting for more than 30 years worldwide. So let's get started. Okay, so here's the agenda. Um, what I have done is put the whole lecture in 7 paradigms. And the reason for putting them in paradigms are words of wisdom collected through experience of years. And that's what I'm putting my years of experience here. And another reason for doing that is that when the things go wrong, we don't know who to blame. And like for example, recently Ford Motor Company paid $5 billion for a recall, and they called it warranty cost. Is it a warranty cost when the product is recalled for sudden acceleration and things like that, and people die from that accident? It's a safety cost, but it doesn't go into the safety budget more or less. It goes into maybe general budget special for warranty cost or something else, or maybe even safety. But most of the time, there is no one is responsible. Why do I say no one is responsible? Because these things are done by teams, a large team of 15, 20 people. And when you say the team is responsible, to me, no one is responsible because someone has to be primarily someone has to be primarily responsible for doing right things right the first time. That's the gist of my lecture. Doing the right things the first time, and of course, you blame the right person also, or even if you're blaming the team, you can still blame the right person. Who's the right person for the team? The team leader. The team is doing what the team leader tells them to do. So very rarely any responsibility is assigned to the right people. Okay, so next week, so in the agenda we are talking about why we design for safety, and I will call it system safety because it's the safety of the system, not safety of a sub-function or subsystem. It's of the entire system, which includes customer, maintenance people, repair people, everybody. Then I'll go into a little bit about reflection on the current state of the art. Then I'll cover 7 paradigms, and I'll go through each of them in a lot more details. So what happens is the reason we design for system safety, like I mentioned, is the safety of the whole system. So we have to take a systems approach. Systems approach includes many interactions within the system, outside the system, organizational interface, and company connections, and including system users and interactions of the users. So there's nothing independent there. Everything is dependent on each other. So when all connections and interactions are properly working together to accomplish a shared goal, we can get tremendous results. Okay, so when we say working together, again, let me emphasize who's the person responsible for making them working together? The team leader. Okay, now Another reason we design for safety of the system is that we have to prevent recalls, accidents, and recalls are costing billions of dollars. Even Toyota companies famous for safety and reliability. They have millions of cars recalled because of sudden acceleration. Suddenly, the airbags come out while you're driving at 70 miles an hour, and so on. So, so we have to have much broader outlook for the system itself. So, in the product development, system safety is very valuable because there are not only a lot of challenges for safety engineers, but also a lot of challenges for the design engineer. And to me, in my experience of 30 years, I can tell you that safety engineers are secondary because they look at the specific, they take the specification and work from there. The primary problem is this is about 60% requirements are missing in the specifications, especially related to safety. So if this 60% things are missing in the specification, how can you make it safe? There is no way you can make it safe. So, so the challenge is not only make the safety engineer responsible, but before you make the safety engineer responsible, make the design engineer responsible for writing good specifications. That has to be the first thing and done right. If you don't do that right, nothing else will be right. So just keep that in mind. So if the design engineer leaves out 60% requirements, nothing else can be right enough for safety. So the word system safety came up from the aerospace organizations, and they have a society called International System Safety Society. They are the ones who promoted this concept of systems safety of the system rather than just the individual components and subsystems. But unfortunately, they started promoting this concept 50 years back. And still, it's an obscure thing to see. Very few companies, especially not in those companies not in aerospace, they use the word system safety. And it should be used everywhere, even in hospitals. The system has to be safe to keep the patient safe. But to give you a hospital example, one of my friend's wife went to cut left leg, they cut her right leg. Okay, so now if you're analyzing for safety what happened, you can come up with the solutions that are very, very cheap if you do it very early. Okay, so if you question, so you can question during safety analysis, how can the leg be cut wrong leg? How can the doctor cut the wrong leg? Well, one reason could be that the nurse marked the wrong leg. And if that and that will be that's the usual reason. Okay. And why would the nurse mark the leg wrong? There's a technique called fault tree analysis. And these questions are asked in this manner using that fault tree analysis. So I'm sure you know about most of them, most of you. So, so the second question is why would she mark the wrong leg? How could she mark the wrong leg? Well, because she's doing it before the surgery when the patient is sleeping under anesthesia. So patient cannot tell which leg is being marked. Okay, so what's the solution? That doesn't cost practically anything. The solution is mark the leg when the patient is awake. That's all. It doesn't cost any money, extra money. Just the timing of marking the correct leg. And same thing happens can you with your eye surgery, which arm to cut, and so on. So, so that's where safety starts. You have to be vigilant. What should have been done? I mean, before you do anything, any process, before you design anything, before you do analysis of anything, and these questions have to be asked. So, so another challenge is our systems are getting complex every day. New technologies, new software, new new connections, new internets, new cloud computing devices, and so on. So so we have to keep track. We cannot keep track of all the changing technologies, but so so what we have to do is instead of worrying about only one system of your system at a time, we must worry about what we call even broader concept, system of systems. Because even though you are designing a, let's say, that aircraft engine, and but you are dealing not only with the engine systems, but you are dealing with the complex software with million lines of code in each flight control. And so how do you analyze million lines of code? It's very difficult. So you're dealing with system of one system is the hardware, another is software, then another could be internet, third could be a technology tools. So you are really should be calling it safety of systems. That will be better word for this class. Talking about system of system flight control software, I did consulting for Boeing, and I went to Seattle to help them on Boeing 777. I asked them how many, we were analyzing flight control software. And I asked how many how many lines of codes go into the flight control. They said more than 1 million lines of code. Okay, you cannot use typical tools like fault tree analysis. You can do analysis to discover some problems, but most of the problems will be still hidden there. And same with the FMEAs and design reviews and so on. So you cannot sit down and find out all the different paths that intermix with each other. And it's not only lines of code, these lines of codes react with other lines of codes, and you can have 2 or 3 million combinations. How can you analyze 2 or 3 million combinations manually? You cannot. So the question is, what do we do? Okay, one team member suggested, well, why don't we have a redundant flight control systems? And like one team could design the flight control system, another team could design to the same specification, but totally independently. So the two softwares are totally different for each. Of course, I'm assuming the specification was right. And okay, so everyone protested the cost will double because if two independent teams have to design two independent million lines of code, the price of the software will double to a few millions, maybe $4 or $5 million instead of $2 million. Okay, so but he explained that if you prevent one accident on the Boeing 777 aircraft, your savings will be 100 times more than what you spend on this designing 2 codes of software. Well, they agreed to do that. Okay, then you don't stop there. You have to keep asking questions. What if they don't match? If the answers of each flight control don't match? Well, then the choice is you shut down the flight, don't fly, and until you solve the problem, and that could take months. So the final idea was, let's have 3 teams developing independently 3 different codes, each more than a million lines of code, and 2 must match to fly. So if the 2 match, that means chances are though very good. It's the right output because both teams were completely independent. Okay, finally they agreed that the solution is the best solution. The cost will triple, but it's still worth it, even if one accident we prevent of 500 people on the flight. So they have finally adopted that solution, and it worked very well. Okay, so you can see how complex this scenario can get. Okay, so let's look at the some more. Now let's look at some more information. Inadequate specifications and requirements to continue to do the process are usually a problem. We must learn how to write correct specifications right the first time. And that requires tons of brainstorming, a lot of brainstorming. And don't write the specification and just take it to the final design review and approve it. No, analyze before you tell anyone about approving. So, that's continue to be the big problem. The management of change is another weakness in the systems, because so now we are finding one problem at a time. We are making a change. We don't have the budget. Big change. When we make $1 million change, you don't have the budget. And then you people start taking shortcuts or start ignoring the problems. So we must say, well, now once we make the change, you have to make sure the change itself is not creating new problems. You have to watch out that also. So you have to brainstorm what can go wrong with the change. And again, another fault tree to do what can go wrong with the change. So make sure they don't cause new unintended consequences. So now people blame human errors in use to create accidents, soft maintenance mistake, repair mistake, use mistake, but remember, user cannot cause the accident unless there's a hazard already in the design, unless the design is vulnerable to that human actions mistakes. So when you think about all the mistakes, you have to make sure design doesn't allow you to make those mistakes. Then human factors don't matter. So to understand how the accidents happen, you have to understand that 2 things must go wrong. One is there is a vulnerability in the design that lets you make mistakes. That's called hazard. And others called trigger event. And so hazard is there. It doesn't let the people make mistakes. But if the design was vulnerable, accidents will not happen unless humans make mistakes. So human error is called trigger event. The vulnerability is called hazard, and human error is called trigger event. It's like a bullet. If your bullet is loaded, it's a hazardous already. But trigger event is unless someone shoots on that device. So let's look at some paradigms. Paradigm number one is always aim for zero accidents. Now, to do that, a famous book written by Philip Crosby, former senior vice president of ITT Corporation. He wrote the book Design Quality is Free. Okay, that's his idea of making quality free. Design right the first time and do everything you can. And of course, this concept definitely applies to safety. Actually, he was my client also. I did some training for him when he was senior vice president. He wrote the book after he left the company, became a consultant. So, so read that book if you can get a chance. Quality is free. It prevents defects and errors and shows you how to not to make those mistakes by doing the right things right the first time. Again, it's not so very simple. It takes a lot of effort to think about what errors can happen, what things must happen right to do it right the first time. And like one of the major incidents, one of the major causes I'll keep repeating is write good performance specifications. Don't miss out 60% things out of it. Typically, I go to the companies, I find 300 or 400 mistakes in the, I mean, 400 things left out in the system specification. And so we have to go through 300 or 400 changes in the specifications every time I go to. I'm talking large systems like cars, trucks, engines, and software, and so on. So the overall effect of zero defect is your company will be very highly profitable. We are talking about 10,000 to million times return on investment, but minimum 1,000 in return on investment you can expect in anything. Okay, so if the solution doesn't cost anything, you have more than 1,000% return on investment. Just like I talked about the hospital area, that mark the right leg when the patient is awake. The return on investment is zero, so return is many. No lawsuits, no killing of patients, no insurance claims to be paid, and so on. So return on investment is tremendous on solutions like that. Okay, we are still on paradigm number one. I'll talk about Michigan company that I was consultant to. Uh, they made heavy duty trucks in Kalamazoo, and they were designing electronic transmission for it. And there was a shaft and a gear assembly that failed every 2 or 3 years. And the truck drivers don't expect a failure at least for 10 years. So we decided to design for 20 years instead of 10 years. And, and the cost was hardly any cost because the solution was just to change the heat treating method. There was heat treating process already going on with the shaft and gear assemblies. All they did was change the cooling and heating rate, and that changed the product to 20-year life instead of 10. And okay, so now when you talk about life, you're talking about, most people talk about average life. Don't aim at average life. Aim at minimum life, not average. Average means you are willing to tolerate 50% failures when you reach the average. That's not what we want. So remember this good example. just by changing the cooling and heating rate, you change the strength of the assembly. The paradigm number two is learn to say no. And so when you feel the specifications are not analyzed properly, vote no. And I just speak up. And I ask them to brainstorm. And so without good risk analysis, you cannot have safety. So you have to question everything. So during the system development, you have to usually say no to it many times. But whenever you see the possibility of not an analysis not good enough, you should learn to say no. Now don't approve that analysis. So many organizations have final design review where you get final chance to speak up. Some call it critical design review. Well, you should speak up if you don't think they have done enough good job to do it right the first time. And then, believe me, you can easily come up with those questions. So, so the context, the paradigm, another minor paradigm we have to remember here is if everyone says yes, your answer should be no. That means they didn't think about the problems and they didn't think about brainstorming the specifications and so on. So, because there are always problems, new problems in the specifications and in the minds of the team members, and since they don't speak up, we should take some action. They probably think it's too late to interfere, so they don't ask. And in fact, that's what happened to me on this truck design team I worked with. And I asked them to come up with the problems during brainstorming. They came up with about 20 problems, 20 to 30 problems. I said, that's not good enough. There should be at least 100 problems. And so I gave them 2 weeks. And in the 2 weeks' time, I told them to take a long shower. Why long shower? Because when you take a long shower, and I told them not to think about the solutions, just think about the problems, okay? And and the solutions will come by themselves. And believe me or not, 2 weeks later, we had about 300 problems brought up and about more than 100 solutions. And the solutions they didn't even look for, they just appeared because your mind is calmed down when you take a long shower. And that's why that's how the mind works. If the mind is calmed down, it can come up with the solutions very easily. In fact, that's what happened once in a company I worked in Milwaukee. And that time I used to work for GE before I joined this company. This company had a lot of problems. There were problems. They were going out of business because they make big transformers for shopping centers, and if every time transformer fails, the shopping centers had to be shut down for 2 or 3 days. So they lost more than 50% customers. They were about to go bankrupt. That's why they hired me, because someone recommended my name to them that they need to improve reliability. I was a reliability engineer at GE that time. Okay, so we looked at the problems and big thing, we looked at problems and we came out a lot of design problems. Then we identified 20% design problems responsible for 80% cost, and we solved those 20% problems. And we were able to design for minimum 15-year life, not 2 years. Minimum 15 years. No, nothing should fail before 15 years. And we had data on accelerated life testing to prove that. we went to our customer, Con Edison in New York, and explained to them that we got now, they shouldn't be afraid to buy our transformers for shopping centers because we have solved this problem. And we showed them that there's been no failures for 15 years. You know what they told us? My president of the company went with me, and they told us, get lost. You guys come and tell me you solved a problem each year, and next year there's a new problem. So we don't trust you. And then my president came home back to Milwaukee and said, Dave, what do we do now? They don't trust us. So I gave him the same solution. Take a long shower for a week or two. Solution will come by itself. Guess what? Next day he called me. He congratulated me on the phone. He says, Dave, we got $25 million order from Con Edison. I said, how did you do that? He said, you told me, just take a long shower. The solution will come by itself. Yeah, the solution is, I took a long shower and the solution was, if they don't trust us that our product will last 15 years, I gave them 15-year warranty. And everything loss related to failure will pay. And they brought the concept right away and gave us $25 million order on the phone. Now, this progress did not stop right there. The Con Edison told other power companies also about this, and suddenly we got most of the customers back within 3 months. And this company made at least $60 million profit on that investment. Just solving few problems and doing accelerated life testing. And this company became so profitable, the other big companies bought us up and at a very high price. So, okay, make sure you speak up. Team members, they don't speak up, they should. Okay, so another example of Ford Motor Company is that the vice president of Ford Motor Company was new to the company. Everyone had 10 years experience and they saw, so they were working on Lincoln Continental car. And he insisted on doing everything right from the beginning, brainstorming everything. And even though everyone had 10 years experience, they objected to it, but he kept insisting. The result was that redesign began 4 months late. The new model of the market on the market was ahead of schedule, 1 month ahead of schedule. He made 700 design changes, and actually they finished the project using only a third of their budget and came out ahead of schedule, and they saved $60 million savings in the future costs. That's how systems should work. Okay, the paradigm number 3 is, I already mentioned, make significant effort on system requirements analysis. So making one change at a time is bad. That's called scope creep. And results in expensive changes later, results in many shortcuts, people taking shortcuts and so on. So robust changes cannot be made if you have got bad requirements. So ask the questions, what kind of functions could be missing? Do we need a modularity in the software to prevent a lot of interactions in the software? Do we have good specifications on reliability, safety, serviceability, human factors, and so on? Do we have enough specification coverage on the interoperability functions, such as on internal interfaces, external interfaces, hardware interfaces, user interfaces, and so on? Also, we need to finally ask what to address if there is an unexpected event, such as power failure. And there will be accidents because there's a power failure. Or suddenly there's a big storm and so on. And So you have to question unexpected events also. And there's an analysis technique called sneak circuit analysis. And that's what they aim at, unexpected events that sneak in without your knowledge. Okay, also make sure you identify the functions a product should not do, like sudden acceleration and sudden explosion of airbags and so on. And make sure you include a range of applications, not only in US, but if the product is going to be used in Saudi Arabia and so on, different environments are there. Make sure your design includes servicing coverage of servicing mistakes, so this should not cause any accidents. Same with the logistics requirements and manufacturability requirements. Paradigm 4. Prevent accidents from single as well as multiple causes. That's pretty obvious. Okay, so not only look at single causes, but sometimes two or three other things have to happen together to cause an accident. And fault tree analysis can give you that idea. Which are the three other things that can cause accident? Also, they must happen at the same time. You don't usually expect them to happen at the same time, but they could. So, so make sure your risk analysis completely covered, and including the fault tree analysis, which can tell you combination of causes that can cause failure, not just single causes. Sometimes it's a combination of causes a failure. So remember, you have to either to prevent accident, you have to prevent two things: to prevent the latent hazard in the system vulnerability, and prevent the trigger event human error, which is human error. Okay, so let's take care of our NASA Challenger accident, where oil, they were not supposed to fly below 40 degrees temperature, and unfortunately that day temperatures below 40, and because Ronald Reagan was going to visit the flight, the management decided to take a chance, fly below 40. And below 40, what happens is the oil seal, it freezes and starts leaking. That's what happened, and several astronauts lost their life, including the whole shuttle collapse. And the solution in this example was that you design the seal so it doesn't freeze at any temperature. All you needed was one heating element to keep it warm below 40. And that cost will be less than $1,000. And nobody had thought about doing that. And that's because the design was not challenged enough. Okay, I covered in the heavy duty truck also heat treating method to do it, prevent the whole accident and just about at very little cost. So to do right the first time, you have to follow these four principles. Change the requirements to avoid the hazard, not only accident, but hazard and a trigger event both. Introduce fault tolerance. If you don't have complete solution, make sure you have redundancy. Just like flight control system, we had put triple redundancy on the flight control software. And if you cannot still prevent the accident, design to complete the mission safely. That means if it fails, it fails in a manner that's safe. And if it cannot do that, then use prognostic health monitoring system to give warnings of things going wrong before they go wrong. Simple. Okay, so I just talked about prognostic health monitoring system. That's a paradigm number 6. Always use that in a complex system because you want to predict accidents before it happens. And and systems should be designed. This prognostic health monitoring system tells you well in advance. It tells you how much the remaining life is for that problem, if it's not going to fail immediately. And it gives you wear out effects, and it can even shut down the system safely. So this technology detects failures before they happen and gives warnings and prevents accidents before they happen. Very important tool. Now, unfortunately, people don't think about that prognostic health monitoring much because they don't think about many problems. I went to a workshop, FAA workshop with NASA, and they looked at American Airlines. They had about the NASA file showed, I mean, FAA file shows 103 problems with this flight, and approximately two actual, and in the American Airlines own files, there were 260 problems identified. And then the American Airlines asked their employees to report the problems. They reported 13,000 problems versus FAA reported only 130. So you can see there are so many sneak failures in the system. You have to be ask employee suggestions and things like that, and they can report more problems than you know. Okay, problem paradigm number 7. Always analyze the structure and architecture for complex systems, especially in software. You tweak in one place, you get problems in 10 other different places. You may not even know for which 10 places made a change. So as a result, there are latent hazards are there in the system always. So, so this structure means structure is something in the software doesn't change. Usually it's a structure called top-down structure, but everything communicated downwards, no sideways. So it minimizes interactions. Architecture is within this each branch. How do you prevent interactions, minimum interactions with other modules, and uh, and so on, mainly minimizing interactions by modularizing the design. So each module has few lines of code and it doesn't communicate to too many other modules. That's called modular design. So, so that's what I've talked, just gave you an example of modularity. Okay. So unfortunately, by the time safety people get involved, the structure and architecture is already designed by the software engineers, and involvement is too late. Not much you can do about it. So make sure the structure and architecture safety design is done with the architectural engineers, software architecture engineers. Okay, so now let me. I gave you the big picture. Okay, and I want to make sure that we understand again. So let me repeat some of those paradigms one by one and by going all the way to the top. Paradigm 1 is always aim for zero accidents. That means we have to analyze so accident cannot happen. Paradigm 2 is be courageous and just to speak up. If all vote yes, you should vote no, because that means they did not ask any enough questions. And I have gone through so many teams, and this happens all the time. So, so, but it's so remember the rule. If the people are not coming with a lot of questions, what should you tell them? Anyone remembers? go home for 2 weeks, take a long shower. And during long shower, questions and answers both will come to you because your mind is calmed down. And this is a good advice for training. In the training, you use this tool. And so what happens is you become creative when your mind is calmed down. So, so, so before you even begin the design review, tell people to take a long shower the day before that. And then come to the design review and tell them the goal to think about, to don't think, just let the problems and solutions come to you. You write them down as soon as you finish the shower. Or speak to your computer while you're in the shower so you don't forget to write down. You don't have to remember what to write down. Very important tool. I gave you the example of 15-year warranty. And the president took the shower, gave the customers 15-year warranty, and he got $25 million orders right away. So can you see the return on investment already on these things? Okay, so another thing is you have to spend significant effort on system requirements analysis. And I have to struggle with this quite a bit. And every team we made at least 300 or 400 changes in the last large systems. In fact, what happened, the chief engineer, uh, he took my course at Society of Automotive Engineers about this course, and he invited me to be the safety consultant to them. And the minute he left the company, we used to have a lot of hours of brainstorming on the system requirement specifications. The minute he left the company, they hired a new vice president of engineering. And this person, she was very good, knowledgeable, but she did not believe in what I said. And because she had not experienced like others, and she wanted to cut budgets. And one of the person to be cut budgets is me. So that's how after 4 years, I was let go because she had no experience in these things, and she wanted to. Our first job was to cut the budget, and she figured if they all had taken my training anyway, why do they need me? Okay, it was short-sightedness, and I don't know exactly how they performed after I left, but I got a feeling that for some time they must have performed right, and then they must have started degrading because there's no leadership. Leadership was not guiding. So, so next paradigm is, of course, will be done in a couple minutes and prevent accidents from single as well as multiple causes, especially pay attention to multiple causes. Sometimes single thing doesn't cause a problem, but two or three things that happen at the same time can cause the problem. Like you have redundant system. If both the redundant systems fail from this accident, you might think that you've done a good job of providing redundancy, but remember both the redundant systems can fail also. Even triple redundancies can fail. Yeah, Boeing 747 Max recent accident had those problems. There is a triple redundancy in the software that failed also. And then the flight control crew cannot control the plane because the software kept cutting off what they did. So, okay, paradigm 6 is the use prognostic health monitoring system to predict the accidents, warn about the accidents much before it's going to fail, and or even prevent the accidents. And paradigm number 7 is always analyze the structure and architecture. And I think I spoke to you on that. So now let's go back to final slide. So we have to make sure that taking a system approach enables you to take the internal and external interfaces correctly, interrelated organizations, functions, and all connection interactions analyzed properly. And don't try to just analyze one function at a time or one subsystem at a time. Try to analyze multiple systems. Well, first you can of course analyze subsystems, but then you do complete multiple systems analysis also. So, well, all interactions are properly working together to accomplish a shared vision. We can achieve tremendous results. Engineering can get a tremendous credit, and I have seen this happening all the time. So just uh, pay attention to those 7 paradigms. And good luck to you. And if you have questions, please I'll
Yeah,
request Daryl to
yeah.
communicate the questions. Thank you very much.
Right. Thank you, Deb. We appreciate the presentation. Right now, I don't see any questions in the chat pod. I'll ask again if those people are attending, if they have any questions, please type them in the chat pod. While we're waiting for that, I'll just also say that please, IEEE USA has a number of upcoming webinars in April. If you could look at our IEEEUSA.org website to see what future websites we hope you can attend. Deb, I'm not seeing any questions, so do you have any final remarks?
Yes. Yeah, if you have questions crop up later on, you can write to Daryl Griffin. He can pass on those questions to me. I'll be glad to respond to you.
Yes,
Doesn't have to be today. Can be after a day or two also is okay.
yeah, cool. Yes, that is certainly correct. My email address is actually on the email invitation that you received today. So yes, if you have any future questions, please feel free to send it to me, and I will connect you. I will send it to Deb for his response. I want to thank everyone who attended, and I want to thank Deb again from IEEE USA for presenting this informative webinar. And right, that's about it. So I'm going to end the webinar. So I will see everyone later. Deb, thanks again, okay? And thanks everyone. Bye-bye.
Thank you.